Hello everyone, we're Team 5 and we're going to present about our final project for machine learning, which is Shopee price matching. So first, let's take a look at the problem. So with the development of e-commerce platforms, people go shopping a lot nowadays. As a result, the retailers want to collect the prices of the same product from many other shops in order to offer the best price to attract customer. To help with this, we develop a system to solve the product matching problem. Next. So there are two big challenges with our problem. First of all, as we don't know how many products are there, the number could be very large, and the image classification problem is not applicable enough. And secondly, the machine learning model needs to learn how to recognize images and differentiate them, even though the product is never seen before during training. So about related works that we base our project on, first, it is feature learning, which helps improve a lot with the task of vocabulary, speech recognition. And secondly, it is FaceNet, a Siamese neural network that was able to directly learn the mapping from face images to a compact Euclidean space.
32,400 numbers of posts are used as training dataset with metadata file and image file. EDA is important in this project to help us gain some first insights about the data.
We'll talk about the methodology of our project. Feature learning is a set of techniques that allow a system to automatically discover the representation of the raw data. It can be either supervised or unsupervised. Next, to enforce feature learning, we apply CMS neural network that use the same weight by working on two different inputs to compare comparable output. The architecture of the neural network used in our project is built on an image classification model, removing the last classification layer. Learning in CMS neural network is enforced by the chiplet loss, which requires three inputs, an anchor, a positive, and a negative sample. The goal of this loss function is to minimize the distance from the anchor to positive while maximizing the distance from anchor to the negative. The equation of the chiplet loss is as shown in the slide, where F is a CMS neural network and alpha is a margin threshold between positive and negative pairs. Next, there are three categories of chiplets: easy chiplet, where the loss is zero; semi-hard chiplet, where the positive is closer than the negative but still within the margin; hard chiplet, where the negative is closer than the positive. Next, there are two different types of chiplet mining, which is offline chiplet mining, producing chiplet offline, for example, at the beginning of each epoch, or online chiplet mining, which compute useful chiplets on the fly on each part of inputs. It's noted that we need to ensure there is at least a valid chiplet for each input. Next, in our project, we use online chiplet mining, and there are two strategies to calculate chiplet loss on each part. First, batch order strategy, which select all valid chiplet and calculates the average loss of the hard and semi-hard chiplet. The second strategy, batch hard, which selects the positive farthest a sample away and the negative nearest away to the anchor. The batch hard strategy yields the best performance and thus being used in our project. Next, the feature embedding generated from the trained network will be normalized and then fit to a KNN model to find the neighbors of each embedding. The neighbors with distance to the reference embedding less than the threshold, which will be considered a mask with a reference image. Next, we can also use an MNP model to extract feature embedding from text based on the title field available in the dataset. The feature embedding can be a simple TF IDF vectorizer or a contextual embedding.
Since the title contains many languages, we try to utilize multilingual text model. The model is trained on Wikipedia in different languages. We experiment 3 text encoders from Hugging Face as well as non-contextual TF-IDF to extract vector embedding. This is a general structure of our model. After we initialize text model and tokenizer, We utilize dense vector from last hidden layer by mean pooling. For the final evaluation, we use quotient distance or KNN to compare distance between embeddings. F1 score is the metric in our experiment. As we can see, by combining different model output, we can achieve much better F1 score. However, overall, contextual model like BERT performs not so good compared to TF-IDF. The reason for this might be the fact that we're only extracting embeddings from the last layer. This will be heavily biased towards the actual task of BERT. Therefore, it might make more sense to take the average of embeddings across all layers rather than plucking the embeddings of the last layer.
Next is the main part of our work product. We load the CMS neural networks with pre-trained weight on image, extract the image embeddings, feed them into KNN and get a distance threshold of 0.6 to be the optimal distance. From the result on the table, the pre-trained networks show excellent score on image matching problem. We fine-tune this model by training with 3 lots. Each is trained with 50 epochs, proper optimizer, and hyperparameters. The training results are shown on the table. All models improve their performance after fine-tuning up to about 11% of F1 score improvement. The Bayesian transformer model yields the best result. They can be overfit on ResNet 101 and EfficientNet be 0 because they yield lower score than ResNet 18 on the problem, while get better result on the ImageNet. In conclusion, pre-trained CMS neural network achieves excellent results and can be improved by fine-tuning, and feature embeddings from images yield better results than that of title. That's the end of our presentation.